Hello everybody. We're going to do relative humidity today. Right here, relative humidity. What is relative humidity? That's the amount of water vapor in the air in relation to what the temperature of the air at that given moment can actually hold. What's the maximum amount of water vapor it could hold? And we have a little definition here. We'll try to make it clearer by showing you this. The amount of water vapor in grams in the air at a given moment, and you divide that by the maximum amount of water vapor a given air temperature can hold, and that's also in grams. Grams cancel out, and you get a number which you can multiply by 100 and get a percent. If you've done it right, you always have a number less than 1, which you then multiply again by 100, and you get a percent. Relative humidity is always reported as a percent. So let's take a quick look at how the amount of water vapor a given air temperature can hold does vary. We have a table here, and this table shows pretty clearly. If you look at the right hand column, you see the amount of water vapor. And if you look at the far left, you see temperature in degrees centigrade. And you'll notice at the top, the temperature is very cold, and the amount of water vapor that very cold air can hold is very, very little. And then as you drop all the way down to the highest temperature, I think it's 40 degrees centigrade, you'll notice that temperature air can hold 47 grams. Huge amount of water vapor is in the air when it is warm before it reaches saturation. That's why summer days can often feel so humid. And that's why when it's raining or snowing in the winter, you don't really notice the humidity. So let's do a little experiment with these jars, containers. We have 250 milliliters of water, which we're going to just pour in these different temperature airs. And the different sizes are representing how the different temperatures can hold more water vapor. But we'll always keep the amount of water vapor, in this case blue liquid, the same. So let's start with a temperature of 15 degrees centigrade. And at this temperature, we're going to say that the relative humidity is 50%. Now, why would that be? Because half of the air is filled with water vapor at this temperature of 15 degrees centigrade. But if we raise the temperature, we change that relative humidity, and you can see it illustrated by putting the same amount of water vapor into that hotter air, a bigger jar representing the warmer air. And you can see the relative humidity drops down. We've gone from 50% to 25%. Now, a jar representing 40 degrees centigrade air and the same amount of water, 250 milliliters, and we lower that relative humidity by half again. Now we have a hot, dry, desert condition. Hot and dry air. 12.5% humidity, 40 degrees centigrade air. And again, going back down in temperature, we watch the relative humidity go up. Now we're at 25% at a temperature of 25 degrees centigrade. Now we're at 50% at a temperature of 15 degrees centigrade, the average temperature of the Earth. And now, at 0, freezing point, we have reached a relative humidity of 100%. And that tells us that it could be either raining or, in this case, snowing. But we're right on the border here. Chances are it's not a super duper snowstorm. It might be. Well, that's actually, we shouldn't say anything about that. But let's look at our last example. Our last example, we have a container where the temperature is negative 10 degrees centigrade. And this same amount of water vapor suddenly enters that air. You see that we have a huge event, rain falling everywhere on these poor little creatures. Actually, it wouldn't be rain, it would be snow, it would be a blizzard. We've reached saturation. And so that, my friends, is the story of relative humidity. As the air temperature goes up, if we have the same amount of water, the relative humidity goes down, same amount of water vapor in the air. And as the temperature cools, that same amount of water vapor can reach saturation and cause precipitation.